In today's example with discrete random variables, we are going to be working with negative x values. An insurance company offers fire protection policies with a face value of $90,000. The company analyzes claims X of $30,000, $60,000, and $90,000 and obtains the following probability distribution. So if claims are being made in these amounts, that means the X value is a negative number. We also could have 0 claims. And here are the probabilities associated with each of those claims. What we'll need to do in order to find out the expected value or the mean for these claims is to fill in this table, and that will help us to organize all the information we need to calculate the expected value and the standard deviation for this information. So I'm just going to take the given x values and place them in the column for x. So we're going to have our negative 90,000, negative 60,000, negative 30,000, and 0. The probabilities associated with these values are as follows. The negative 90,000 is 0.001, and that is the same for the negative 60,000. We have 0.004 for the negative 30,000, and 0 is 0.994. In order to complete the XPX column, we're multiplying the X value of negative 90,000 by 0.001, and that gives us negative 90. For the next product, we have negative 60, and then we have negative 120, and 0 times 0.994 would be 0. In order to complete the last column, x squared px, we first need to know how much x squared is, and this is where we're going to work carefully. If we're looking for x squared, that means we're taking the entire quantity of x and multiplying it by itself. So we would have a negative multiplied by a negative. So that means the x squared values should always be positive numbers. So our first x squared value would be negative 90,000 multiplied by negative 90,000, and that gives us 8,100,000,000. Negative 60,000 squared would give us 3,600,000,000. Negative 30,000 squared will give us 900,000,000, and 0 squared will give us 0. For the final column now, we're taking the x squared value, multiplying it by the probability, and then we'll write it in the last column. Our first product is 8,100,000. Our second product then is 3,600,000. Our third product gives us 3,600,000. And our last product is 0 times 0.994, so that's also 0. Now that the table is complete, our formula for the expected value is the sum of the XPX column, and that equals negative 270. So to interpret that value with a negative number, that means the insurance company can anticipate an average loss of $270 per claim. So any negative result is going to be a loss of that many dollars per claim. For part B, we're looking for the standard deviation. In order to calculate that, we need to find mu squared and the variance, which is sigma squared. And we'll substitute those into this given formula. So to start with, mu squared is equal to the quantity of negative 270 squared. So remember, a negative times a negative will result in a positive product. And this product is 72,900. So we do have our substitution now. for mu squared, and we know that the sum of x squared px can be found by adding the values in this last column. So our sum of x squared times the probability of x is found by adding this last column, and that will give us 15,300,000. So that is the substitution for the sum of x squared px. To make those substitutions, then sigma is going to equal the square root of 15,300,000 minus 72,900. And don't forget to take the square root. When we do the subtraction, we're going to get 15,227,100. Once we take the square root of this amount, that comes out to about $3,902.19. Since it is money, we should round this to 2 decimal places to represent to the nearest penny. For part C, we're looking for the minimum and maximum value for the interval mu plus or minus 2 sigma. In other words, we're interested in the interval that falls within 2 standard deviations of the mean. And we'll write our answer with interval notation, and that would be from the minimum value to the maximum value. So we recall that mu is negative 270, and the standard deviation is 3,902.19. So that means negative 270 plus or minus 3,902.19. So we'll start with the lower end, or the minimum value, negative 270, and subtract the standard deviation. And we'll get negative 8,074.38. And then we'll add the standard deviation. That total is 7534.38. So to write that in interval notation, we've got negative 8,074.83, comma, 7534.38. Now that we found the interval that falls within the 2 standard deviations, these are the x values. If we go back to our table and look at the x values, do any of these x values fall within this interval of negative 8,000 to 7,500? So negative 90,000, that's much smaller than negative 8,000. Negative 60,000, also much smaller. Negative 30,000, much smaller. But 0 is an x value that falls between our minimum and maximum value. So 0 is associated with 0.994 probability. So the probability of 0 is 0.994. To turn that probability into a percentage, you're multiplying by 100. So you would have 99.4%. If we compare this percentage with Chebyshev's rule and the empirical rule, we'll be able to make some statement about which rule would be the better predictor for our probability. So our data has 99.4. Chebyshev's rule says that within 2 standard deviations, you would expect 75% of your data. And the empirical rule states that 95% of your data falls within that 2nd standard deviation. So our data came up with 99.4%. 99.4 does meet or exceed 75%, but it also meets or exceeds The empirical rule's 95%. So although both of these rules could predict our data, the empirical rule's percentage is much closer. So I would say that the empirical rule is our better predictor of percentage.